Okay, good morning, everyone. Welcome to day 2 of in-person NVMW. We're very pleased to have as our keynote speaker this morning, Professor Onur Mutlu, who is a professor of computer science at the Swiss Federal Institute of Technology, ETH, in Zurich. He also holds a faculty position at Carnegie Mellon. In addition to his academic experience, he has quite a bit of industrial interaction. He, in fact, started the computer architecture group at Microsoft Research in the mid-2000s. And he's also had positions with Intel and AMD, VMware, and Google. So as he was just telling me, that helps him keep his feet on the ground in his research. He's very well known for his contributions to computer architecture and computer systems. He's interested in hardware security and bioinformatics. And in all of these areas, he's had some very influential papers that have been recognized with numerous awards and accolades. And I can say, as I was just telling Onur, that the series of papers that he wrote with our program committee chair, Eric Harach, and some of his students, Yukai and Yixin Luo, have provided a lot of very valuable insights and information to my own group in some of our research on modeling flash memory characteristics. So he's received a number of significant honors, including being named an ACM Fellow and an IEEE Fellow. And he's a member of the Academy of Europe, which is really kind of the equivalent of our national academies here in the US. So I encourage you to go visit his website if you want to find out more about his research. There's a lot of really good stuff there. And with that, I'd like you to join me in welcoming Onur.
Thank you very much, Paul, for the kind introduction and the nice words. And thank you very much for coming to the talk. Let me try to do something quickly because I don't see exactly that screen, but maybe that's okay. Oh, okay, it's not moving. Sorry about this. Displays. Okay, looks like it's mirrored, but okay, okay, sorry about that. Okay, thank you for the kind introduction. Again, I'm very happy to be here. This is a trip that I made 6 months after my last trip to the US, which was again for a conference. And it's good to have this in-person interaction for sure. So thank you for inviting me also. I'm going to talk about memory-centric computing. This is going to be an intense talk. I have a lot of slides. I don't intend to cover every slide, but feel free to ask questions. Hopefully, I'll give you an overview of what I believe is happening in terms of a paradigm shift in computer systems becoming memory-centric and some reasons for it, as well as some challenges for adoption for much more memory-centric computers that are going to come up. Okay. With that, I think nobody would argue with what's stated over here. Computing today is bottlenecked by data. And data is really key for many, many applications that we design. Machine learning, genomics. I'm going to give you a bunch of example applications and a bunch of case studies that we have been doing, that others have been doing also. Essentially, important workloads are all data intensive. They require rapid and efficient processing of large amounts of data. And this data is increasing on top of this. We can generate much more data than we can process in many domains. And we want to do more sophisticated things on the data as well. And this is clearly limiting our computing systems today. These are some applications. You may be working on them. You may be familiar with them. I think they're quite interesting. And in these applications, data is a big performance and energy bottleneck. And different parts of the memory and storage system becomes a bottleneck at different times. Latency, bandwidth, capacity, they all become bottlenecks at different times, if not at the same time. And when they become bottlenecks at the same time, it becomes quite difficult to deal with it, clearly. And if you look at the mobile end, there are also applications that are quite demanding. They're becoming increasingly demanding. I'm going to talk about some of these applications as well. And you have the same story over there. Data is a big performance energy bottleneck. As Paul mentioned, we work a lot in bioinformatics, genome analysis, and this is an example domain, in my opinion, where data is really growing exponentially. And if you attend talks in genomics, I think people are tired of seeing this graph over here, which basically shows that the cost of genome sequencing has been reducing much faster than the cost of transistor has been falling down, which we believe is clearly falling down fast. But you can see that the technology in genome sequencing is growing much faster. As a result, you have these data generators, genome sequence analyzers, basically, and people have been generating a lot of data in this field. Unfortunately, the sequencing machine is a very specialized machine that can do sequencing of DNA, RNA. But today we process the data that's generated from this very specialized machine using general purpose architectures. And as a result, we're very much bottlenecked in reaching scientific discoveries, medical advancements, etc. Because we need to really, there's a lot of computational tasks to do the analysis of the genome. I'm not going to go into a lot of detail over here. I'll point you to a lot of papers. I think it's fascinating, actually. But this is one application. And this is one example of the data generators. This is, you can see that this data generator fits in your hand. And it's a very efficient data generator, but it's an extremely dumb analyzer. Basically, it has no computation capability. As a result, you have to move the data to the data centers all over the world. And there will be other machines that are analyzing this data. So this is one example of our current systems where we can generate a lot of data, but because we're very much processor-centric, let's say, we move the data all over the place. And this is going to be the theme of the talk. We do this at the macro scale, we do this at the micro scale. As a result, we waste a lot of energy and performance. And memory-centric computing is all about not moving the data, in my opinion, keeping it where it's generated as much as possible or where it's stored and doing the processing over there as well. So if you're interested, you can read more papers. And we've been working on this topic for some time. This is an overview paper that we wrote more recently on this topic. And we actually I'm going to talk about this paper. We've been looking at FPGA-based acceleration of these applications, and bioinformatics is a great example of this. And there are also other specialized accelerators, hardware, software, co-designs, algorithm architecture co-designs that you can do where you can do the processing using specialized architectures near memory again, or near storage. This is a more recent paper where we actually showed that you can do intelligent filtering of genomes or genomic data in the storage device. And that reduces the data moment across the entire system greatly. Okay, so the future is going to be even more, let's say, faster data generators, much more efficient data generators. And if you really want to keep up with this so that we can actually take advantage of these, we really need to rethink our computing systems, in my opinion. And if you're interested, we give talks and we cover a lot in our computer architecture courses, these applications as well. Okay, this was just, in my opinion, a more futuristic application, because if we can enable these devices such that you can give this device to a doctor or a private person, and they basically do the analysis themselves, keeping the data private, that would be very powerful. And maybe you can do real-time analysis where the doctor makes a decision within a minute with these devices, for example, in a life-critical situation. But unfortunately, we're not there yet because, in my opinion, we're not designing computing systems, let's say, right? Because data is overwhelming our machines. Storage capability, communication capability, and in the end, computation capability. You may have a very, very powerful CPU, GPU, accelerator. You're bottlenecked by memory. As a result, you're not really utilizing this. I'm going to show you some results from Google's TPU, for example, with a study, based on a study that we did with Google. This accelerator is quite nicely built. It has a lot of computation capability, but it's waiting idle in many of the Google edge models, as we will see. And in the end, data greatly impacts robustness, energy, performance, and cost. And if we go back to the fundamentals, a computing system really consists of computation, communication, and storage and memory. I put storage / memory. I think it's let's say the same thing in different trade-off space, basically, for the different things. And for decades, we've heavily optimized the computing unit. Computing unit has been the king, if you will. Everything else is secondary. And basically, we're very processor-centric. And this has caused a lot of trouble to us. It's going to cause even more trouble. And this is my cartoonish picture. This was actually from my first NSF proposal in 2008. I drew this cartoonish picture, which basically shows that you have cores. These are the computation units. Everything else in the single node is moving and storing data. Interconnects, caches, other interconnects, other caches, memory controllers, other interconnects, main memory, other interconnects, storage. So if you do the calculation, more than 90% of a single node is really dedicated to storing and moving data. And I didn't even show the storage and movement units inside the cores themselves over here. So this is, I think, interesting to see. We call these computing units, but they're really data storage and movement units. Yet the system is still bottlenecked by memory and storage. So that's where we are basically. And as a result, we're wasting a lot of energy. This is a work we did with Google a few years ago, where we analyzed the applications that I showed you in the previous slide. I'm going to talk about this a little bit more, hopefully. But more than 60% of the total system energy is spent moving data across the memory hierarchy. So in the rest of the talk, I will assume this axiom. I think if we want to build intelligent architectures, and I would argue that we do want to build intelligent architectures, because we're going to rely, essentially, we're going to bet our lives on them almost, in self-driving cars, for example. We really need to handle data well. So that brings the question, how do you handle data well? And I think there are at least three major things to think about. I'm going to mention them. I'm going to talk about especially the first one, because we don't have time for the other two. I think we need to ensure data doesn't overwhelm the components. So how do we do that? We need to certainly look at across the stack. We need to look at the algorithms we're designing. We need to look at the architectures we're designing. And more importantly, we need to look at the entire stack and co-design algorithm architectures and devices together to fit the applications that we're dealing with, in my opinion. So this is going to be the data-centric architecture part. But on top of this, I think there are two synergistic directions I will briefly mention, but we will not have time to cover in the rest of this talk. We have a lot of data that's flowing through the system. We have a lot of metadata that's flowing through the system when a computation is happening. We're not taking advantage of it today. For example, I have a memory controller inside the cell phone. Unfortunately, this is a new cell phone. When my old cell phone was around, I think it's still around, it was 6 years old. That memory controller saw a lot of applications, a lot of memory access flow. It didn't learn anything. Basically, it did exactly the same thing that a human designer dictated to do when it was designed, let's say 10 years ago. Basically, there's a lot of data flowing through the system, and our components are not learning from the data. They're fundamentally not intelligent, basically. Whereas humans, we are very data-driven, right? When I touch a stove, for example, or when my kid touches a stove, they will be upset and they will not do it again. But even if a memory controller is doing the wrong decision at a given point in time, it will keep doing the wrong decision because it has not learned anything. It's not designed that way. So I think this is a critical point. For intelligent architecture, we need to do this. And this also requires computation capability, learning capability, especially in the controllers that we design. I think this is increasing over time, but we need to do a lot more. The third part is there's a lot of data has a lot of properties. And for example, if you look at data, you can characterize in terms of privacy dimensions, security dimensions, approximability, compressibility. I mean, you could keep adding different things. Criticality in terms of computation, even locality. These characteristics are not really expressed at the higher levels and communicate to the lower levels of the stack. Basically, again, I'll pick the example of a memory controller since this is a memory conference, right? If you take the example of a memory controller doesn't know the properties of the data. As a result, when it schedules a request to this bank, for example, what does it look at? It doesn't look at, oh, this data is very important to the user. It doesn't say, oh, this data is security critical, so I should isolate it somehow. What it says is, it just looks at the component. Is the row buffer open? Is the bank busy? Is the bus going to be busy? So it's very component driven as opposed to data driven again. It's not data aware. It's not aware of the characteristics of data. But if we're aware of the characteristics of the data, and if we can communicate it to the underlying stack, we can improve the algorithms and architectures in many metrics. As I said, I'm not going to talk about the second, this one also, but I think this is also going to be very important going into the future. How do we discover the semantic properties of the data? And many of them we know actually. And how can we communicate to the underlying architecture such that our underlying system makes much more intelligent decisions? So this is a slide that repeats what I kind of said in the prior slide. Basically, today's architectures are processor-centric as opposed to data-centric. We're going to talk about how to make them more data-centric. Today's architectures are human-driven. They're making human-driven decisions at the design time, as opposed to data-driven decisions online that learns. And today's architectures are very making component-aware decisions, very rigid component-aware decisions at the architectural level, as opposed to data characteristic-aware decisions. So I think going forward, we will need to change it. And this is the, let's say, blueprint for the architectures that that we have in mind. But to be able to do this, I think we really need to revisit the entire stack. For each of those points that I mentioned, data-centric, data-driven, and data-aware, we really need to re-examine the stack. But hopefully we can get there step by step, because hopefully it's not a daunting task like we're going to change the entire world tonight by redesigning the stack. Okay, this is what I said. Basically, we want to specialize as much as possible and co-design across the hierarchy. And this will hopefully bring us to a point where we can improve energy efficiency, performance, and other characteristics like security, dependability at the same time. Because today we have a trade-off between many of those things. Can we do a lot of things at the same time in an improved way? Okay, so this is a short paper that talks about this position. If you're interested, you can take a look at it, and there are links to the videos as well. So let me jump into this first component, data-centric, memory-centric architectures, because this, even within itself, this has a lot of components, let's say. So if you think about what should a data-centric architecture look like, first of all, I think we're going to talk about the first part, processing data where it resides, where it makes sense, wherever data is flowing, wherever data is generated. Second thing is we need to have low latency and low energy data access. If data is really important, we really need to have that capability, I think, in all of our devices. I'm not going to talk about that, but this is quite interesting and exciting. We need to have low-cost data storage and processing, and there are many different techniques for it. And intelligent data management. We want to have a lot more intelligent controllers handling many different properties of data and many different metrics that we want from our systems. Okay, so we're going to jump into the first one. And I call this processing data where it makes sense, as opposed to just memory storage, because in my opinion, today, basically, we don't have any choice. Our choice is you process the data in processor 1, processor 2, processor 3, accelerator 1, accelerator 2, accelerator 3. You can call them CPUs, GPUs, FPGAs. They're all good, different accelerators, but they're all processors from my perspective. They're not data generators, or they're not data storage units. I think we really need to change that for different parts of the hierarchy. And this is not a new idea. These are some of the earlier papers that are more general purpose in nature. This is, you can see more about 60 years ago, right? Maybe close to 60 years ago. Processing in memory has been proposed. And at that time, it was called logic in memory. This is a beautiful paper, another beautiful paper by Harold Stone. And it has not panned out, but maybe it's going to pan out today. So why should we re-examine this today? And again, I'm going to focus on in memory, but you can think of this in storage, in network, on the line. There are many different parts of it, data-centric in the end, or memory-centric. So I think there are two reasons why today we're kind of in a bind. Technology is pushing us to do something different because we're having a lot of technology scaling issues, especially in memory and storage. And then the applications and systems are pulling us also because we're having a lot of scaling issues at the applications. You can argue which one's worse, but I think if you're the application person, you will see that that's perhaps worse for you. If you're the technology person, you'll see that that's worse. And if you look at both sides, we're really stuck in the middle. So I'm going to talk about DRAM especially, but today DRAM technology is not scaling very well. As a result, people are looking into new ideas. Finally, maybe some people will think that way. Controllers are getting closer to DRAM. Industry is very open to new memory architectures. So if I was giving this talk a few years ago, I wouldn't have everything on the slide, but this would be on the slide. People were looking at 3D stack architectures where you have controllers underneath memory. We're going to talk about that. And people were experimenting with architectures where they could do simple deterministic finite automaton operations in the row buffer. And more recently, people have started actually building near memory processing architectures. This is UpMem, Samsung, SK Hynix announced it at ISSCC this year. Samsung has another work, and Alibaba has another work. I'm going to mention that basically. So today, actually, data-centric architectures are happening. The question is, will they be adopted and will they actually benefit a lot of applications? So we'll see. But let me motivate this technology scaling part relatively quickly, and then I will go to the application system part, and I'm going to talk about some example in-memory computation mechanisms. So this is a paper that we wrote. It was invited to International Memory Workshop some years ago, 9 years ago, where we argued basically technology scaling will require us to rethink how we actually design controllers and systems. And basically it made the same arguments that I've been making right now. So it hasn't changed. But it argued that technology scaling is going to become much more difficult, and we need really intelligent controllers for it. And we also were gathering a lot of data related to this at the same time. So this is one example of data. We worked with Facebook and we analyzed all of the memory areas that they have in their servers. And we published this DSM paper. And it's fascinating, actually. This is a lot of servers. They didn't allow us to publish how many servers, how much memory, because they were concerned it would affect their stock price. But maybe they should be concerned about other things, although they're doing quite well, I think. But basically, the takeaway is, if you do this correlation study on production data centers, there's a very strong correlation between the chip density that's employed in a server and the relative server failure rate. If you really want to understand that metric, you need to read the paper. But hopefully we did the right thing and calculate the metrics correctly. But the intuition is that these devices that are denser are more vulnerable to noise effects. As a result, they have more reliability issues because cells are smaller as well as closer to each other. So you get more memory errors, which is really affecting the service. And there's a lot more data in the paper that I mentioned over here. Okay, we did a lot of other work in DRAM. I'm not going to go into a lot of detail, but this is the RowHammer problem, DRAM RowHammer problem. We studied this a lot, and we showed that you can predictably induce errors in most DRAM memory chips. This is something that should really not happen clearly. In any chip, you should not be able to induce errors. Clearly, you should not be able to induce errors predictably through the software. I mean, of course, if you go and heat the chip, you will induce errors, right? Temperature. But here, we're talking about errors that you would induce by toggling the word blanks. Okay, so if you're interested in RowHammer, I don't have, we have a lot of material related to it, and there are a lot of interesting things that have happened in the RowHammer space. It's a security problem as well as a reliability problem. And more recently, we gave this talk just in 20 minutes. It summarizes essentially what has happened in RowHammer research until 2022, if you will. But this is a scaling issue where you can actually induce errors in real DRAM chips. And I think this is fascinating. So to solve this issue, you really need to have intelligent controllers, in my opinion, at least slightly intelligent controllers. So another aspect of scaling, hybrid memory, that's been talked about in this conference a lot, clearly. This is a scaling problem because some technology is not scaling. So why don't you put multiple different technologies together? It could be the same technology customized in a different way. It could be different types of DRAM, for example. It could be DRAM and phase change memory. You put your favorite technology over here. But this enables scaling, but by enabling the hardware and software to manage the data allocation and movement so that you can achieve the greens of each technology as much as possible while avoiding the reds of each technology as much as possible. But for that, you need an intelligent controller. That controller that sits in between the applications and the memories needs to know about the applications as well as the memories, both the devices as well as the application characteristics. Right. Okay, so that's my takeaway from the technology scaling part. And to solve the RowHammer problem, basically, we've been working on intelligent controllers as well as industry has been working on intelligent controllers over here. Sorry, something came about over here. Let me hide it. And the interesting thing is the industry is writing papers about it. This is one of my favorite papers by Samsung and Intel. It was written in 2014. And I think these companies normally don't even talk to each other. But they did write this nice paper, 4-page paper, where they talked about DRAM process scaling is becoming difficult. And we really need intelligent controls, co-architect DRAM and controllers together to enhance process scale. I can keep going on, but this is another more recent work that we did with DRAM, DRAM that has on-die ECC. And we show that if you have an intelligent control, you can actually discover uncorrectable errors and even correct them online. And I think a lot of people would be familiar here. There's intelligent controls that exist in NAND flash. It's fascinating, I think. And they actually solve the scaling issues. And this is a paper that we have written collaboratively with Eric also. That describes some of the error characterization, mitigation, and recovery mechanisms in SSDs. Okay, so I think I could keep going on, but hopefully the takeaway is clear. We want intelligent memory controllers to avoid many failures and enable better scaling of the technology and the systems. And this is really the push from circuits and devices. Let me give you the pull from systems and applications. And this is, I think this is characterized by 3 things. Data access today is a major bottleneck. Energy consumption is a key limiter, and data movement energy dominates compute. So let's take a look at the implications of this. But before I go into it, I think there are even bigger implications than we may think. The question is, do we want a world that looks like this going into the future, or do we want a world that looks like this? I would argue that we want energy efficiency and sustainability. We cannot give it up. We have to change what we're doing, but we cannot give up high performance also. So we somehow want all of these at the same time. And I think data is the right place to target to get all of those at the same time, because our current design principles from the very bottom up is really causing energy waste. We're moving data all around, right? This is causing energy waste, clearly. This is causing performance loss, clearly. We have recognized the performance loss a lot, and we design our systems to overcome the performance loss. What do? We essentially add a lot of complexity to our systems to overcome the data movement overheads. We add massive levels of multi-threading, software and hardware. We add out-of-order execution, prefetching, huge memory hierarchies. When they work, they actually recover some of the performance loss. Usually they don't work perfectly. Sometimes they don't work at all. If you have a random access application, basically your bottleneck, essentially. As a result, you're compounding the energy waste. So we're in this vicious cycle where we keep increasing our energy waste because of data movement, while trying to overcome the performance loss because of data movement. And there's no way out of it, if you will, if you're processor-centric. And the problem is basically processing is performed far away from the data. So if you go back to the fundamentals again, as I said, processor is heavily optimized. Everything else is doing nothing, let's say, on the data. Okay, so let me give you some performance numbers. This is a well-known problem, clearly, memory bottleneck or storage bottleneck. Right? This is a quote that I like a lot. This is a one-page paper by Dick Seitz, who was the chief architect of Alpha processors in 1990s, which were the fastest processors of their time. After they designed their flagship processor, he wrote this paper saying that it's the memory stupid, basically. He said that we designed this Alpha processor. It's capable of finishing 4 instructions per cycle, every clock cycle. But unfortunately, on this important database workload, it's finishing 1 instruction every 4.7 cycles. So it's operating at 1/18th of its peak bandwidth. And he finishes the article saying that I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. Okay, so fast forward about 10 years, this is my own PhD thesis. We worked together with Intel to analyze their workloads, and we found out essentially the same thing, basically. The flagship Intel processor at the time, on the workload it's designed for, it's waiting for memory most of the time. Okay, you don't believe me, you don't believe Dick Seitz, since everybody believes Google. This is data from Google in 2015. They essentially show the same thing. On a flagship Intel processor at the same time, at that time, Skylake, I think, on their data center workloads, according to them, all of their data center workloads, the processor is waiting for data most of the time. It's really finishing instructions 10 to 20% of the time, the green bars, green portions of the bars over here. And this is a beautiful paper. I'd recommend you take a look at it. So basically, we have a grossly imbalanced system. Because processing is done only in one place, data moves a lot. And on top of this, to overcome the performance implications of this, we make our systems overly complex and bloated. And this compounds the energy inefficiency, complexity of our systems. And also in the end, it makes us even lower performance, I would argue, because you could have used those resources somewhere else if we were not doing the wrong thing in the first place. And as a result, we're back to the picture that I showed you earlier, right? We have this computing unit, but most of it is dedicated to storing and moving data, yet the system is still bottlenecked by memory. Okay, that was a performance perspective. Energy perspective is even worse. So if you go to the energy perspective, this is a nice slide by Bill Daly. The numbers have changed, but the takeaways did not change. A complicated arithmetic operation today is very cheap, 20 picojoules in this number. And this is a success of technology scaling, basically. The arithmetic operation scaled extremely well over 70 years. Unfortunately, the interconnect and memory did not scale well. As a result, there's a disparity of 2 to 3 orders of magnitude in terms of the energy consumption of memory compared to arithmetic operation. And arithmetic operation keeps scaling, even though there are limitations, it's scaling still slowly, and memory is not scaling. Okay, you could argue with that 800x number, but the numbers may be closer to 100x. 100x is still a lot. And as a result, we have this picture that I showed you earlier. More than 60% of the entire system energy is spent on data movement on real workloads. So I would argue that we do not want to move data. We need to change our paradigm to enable computation with minimal data movement and compute where it makes sense, where data resides, and make computing architectures more data-centric. This is easier said than done, of course. In the rest of the talk, I'm going to focus on the memory part. But I think we really need to examine the entire system: storage, memory, sensors, interconnect, figure out what we can do everywhere at computation capability. So let's talk about memory. I think memory is quite interesting, clearly, because it's huge and people actually design applications to fit memory today in memory database, in memory graph processing engines, in memory machine learning engines. Wouldn't it be nice if we actually told memory, could you execute this query for me? And memory returns the results without bothering anything else in the system. It looks nice, but there are many questions over here. How do you design the system this way? Memory controllers, processors, communication units, hardware and software interfaces. I don't think we're at the ideal place. Yesterday's keynote talk was about interfaces, for example. I think we definitely need to do a lot more in interfaces to enable things like this and more. System software, compilers, and languages. How do you adapt the stack? And even algorithms and theoretical foundations. How do you actually redesign our algorithms? So it's really an across the stack problem. I'll mention the theoretical foundations over here because I think it's exemplary of what I've been talking about. If you look at the theory of computing, algorithmic complexity theory is all about counting operations. Basically, it's very processor-centric, right? I think we really need to build a more data-centric theory of computation also, and I don't think it exists at this point. So if we really want to truly succeed in data-centric computing, we really need to build a data-centric theory as well. I'm not the right person to do it, but maybe there are people here who can do it. Okay, so in the rest of the talk, I'm going to give you some case studies and examples of processing in memory. And this, we have written this article that covers a modern perspective of processing in memory. We're going to update it this month also, so there'll be even, let's say, larger number of papers that we talk about across the entire field. If you're interested, you can take a look at it. I'm not going to cover everything that we cover in this paper. So I will argue that we need to think differently from past approaches also. In the past, things were done in processing in memory. Maybe we need to think a bit differently, given that today is different, right, in terms of where we are in the technology scaling as well as applications. So I generally categorize processing in memory in terms of two approaches. One is processing near memory, the other is processing using memory. I'm going to talk about processing near memory, describe it first right now, and then focus on processing using memory. But processing near memory is very similar to the model we have today. Today we have processor here, memory here, they're far away. Why don't we put the processor closer and closer and closer and closer, such that at some point they're coupled with memory. But the processor doesn't change that much in the sense that it's still a von Neumann architecture nicely, and meaning that the programming of this processing near memory will be easier, hopefully. As a result, we're seeing incarnations of processing near memory in industry today. Processing using memory is completely different, and I will go into examples of this first. It can still be integrated into existing systems, but the idea of processing using memory is you have memory. You don't think about the processor. Memory is today designed as memory, but it also has computation capability. The question is, what kind of computation capability does it have? Can we use the analog operational principles that the memory has to also perform computation? Clearly, this is happening in the NVM space a lot. Can we also do it in the DRAM space? Basically, you start with a memory device, but you also realize that it has computation capability. As a result, it's very different from today's systems, but it can be integrated. Okay. So let's talk about the first approach, processing using memory. Basically, the idea is to take advantage of the operational principles of memory to perform bulk data movement and computation in memory. You can exploit internal connectivity that exists in the device today to move data internally and add more connectivity, perhaps. You can exploit the analog computation capability that exists and perhaps make it more robust and maybe slightly change the device to add more computation capability, and who knows what else. I'm going to give you examples from our research where we did this with DRAM. And I'm going to start simple, let's say cheat. There's not even computation, but data copy initialization is actually a big deal also. There are many applications that do a lot of data copying initialization. Imagine initializing a 1 terabyte database. Physically doing this takes a lot of time. And again, if you don't believe me, Google, in this nice paper that I mentioned, showed that just these two function calls, memmove and memcopy, occupies 5% of the entire data centers execution cycles in all of their workloads. 5% is a very big number for just two function calls. It's not the entire data copy initialization in the system. It's not even initialization. Well, copy, it could be initialization. But basically, it's a big number. So how are we doing data copy initialization in memory, from memory today? Basically, if you want to copy a source page, the white page over here to the gray page over here, today you have to go through the processor, at least through the DMA engine, at least through the memory controller. There's no way out. But why don't we just do this? Memory, please do it for us, and the memory does it. So this is low latency. I'm going to show you some results. It's going to be low bandwidth utilization. You're going to save a lot of data bus bandwidth on the most important resource that you have today, perhaps. No cache pollution, but you could eliminate that doing this through the DMA engine today, and no unwanted data movement. I'm going to show you a mechanism that takes a 4 kilobyte page copy from 1,000 nanoseconds to about 90 nanoseconds and 3.6 microjoules energy to 0.04 microjoules. And the idea is very simple, basically. It could be applied to many different technologies, but we did apply it to DRAM. When we actually applied it, we said that you need to change the DRAM to make it robust. But later work in 2019 showed that you could actually do it in existing DRAM chips by modifying the timing parameters and violating the timing parameters. So I'm going to give you the idea. The idea is two consecutive activates. If you want to copy one row, the source row, to a destination row in the same DRAM subarray, which shares the sense amplifiers, you first activate the source row, which brings the data into the sense amplifiers, row buffer. And then you activate the destination row, which implicitly deactivates the source row, connects the sense amplifiers to the destination row, and essentially copies the data that was copied into the row buffer from row A back into row B. So the idea is two consecutive activates, negligible hardware cost. Clearly, this is within a subarray. You can think about, okay, how to do it across banks, et cetera. And we have mechanisms in the paper that I'm not going to talk about related to that. Basically, more recent work by others from Princeton University in a work that they called Compute DRAM showed that you could actually violate the activate to activate timing parameter in DRAM carefully. And you could actually do in existing DRAM devices by just changing the memory controller what we said. And we actually replicated their results, and we found essentially the same thing. I'm going to talk about that. So existing DRAM devices are capable of this. If you want to do it robustly, of course, you need to do a little bit more. Okay, so that's basically the performance energy savings, as you can see over here, and the application level results are in the paper. If you're wondering, okay, what about if the data is in different subarrays, different banks, the paper has results. And we also have a lot of other papers that talk about how to do it more efficiently. And for that, I would recommend you take a look at the lecture that I'm going to point out next. But we more recently released this PyDRAM framework. It's an FPGA-based framework where you can violate the timing parameters of the memory controller and essentially do these copies. And also about bitwise operations, which I'm going to talk about. Okay, so there's more clearly that I'm skipping. We don't have time. But let me talk about the mindset and then talk about block bitwise operations. Basically, the mindset, I think, is we want to think about memory as an accelerator. Memory has capability to do some computation, in this case, data movement and initialization. Why don't we just put it on the memory side? Today, we're building all kinds of accelerators, and they're good at what they're doing, but they're all bottlenecked by memory. Why don't we put an accelerator over here that's not bottlenecked by memory? And it can be programmed potentially similar. Okay, let me talk about in-memory computation a little bit. So similarly, we can support in DRAM and or not and majority at low cost. We're going to use the analog computation capability in DRAM. And the idea is to activate multiple rows. I'm going to show you an example in the next slide. And if you do that, you get significant energy improvements on these block bitwise operations. And here I should mention that it's not just DRAM. Other folks have shown that you could do these triple row activation or N row activation in emerging technologies as well, get similar results like what we have done. But new memory technologies enable even more opportunities, in my opinion, because they're not destructive. Reads are not destructive as in DRAM. You can operate on minimal data movement. And also, because of the structure of the memories, a lot of people are clearly looking at matrix vector multiplication. So that's another example of analog computation capability in emerging technologies. In DRAM, you cannot do that because you don't have the crossbar array structure. But in resistive memories, you can do that. So the kind of computation you can do clearly depends on the technology that you have. And all of those need to be examined, in my opinion. Basically, we need to get out of the mindset of memory is memory. Memory is also computation, basically. Okay, so let me give you what we did with DRAM. So this is called triple row activation. I'm showing you 3 rows over here, only one cell, 1 bit line per row. But imagine that a row is 8 kilobytes, and you may have thousands of subarrays in a DRAM device. So you can do this on 8 million bits concurrent. So if we activate 3 rows concurrently, you connect those word lines to the bit line. And based on chart sharing principles, what you get in the end at the sense amplifier is the bitwise majority function of ABC. So you can do bitwise majority computation. Again, this is proven on some DRAM devices. Even though DRAM is not designed to do this, if you violate some timing parameters carefully, if you're lucky, then you can actually get these 3 rows to activate in real chips, some real chips, not all of them, because not all of them support violating the timing parameters also. You see the bitwise majority function. And of course, bitwise majority is very nice. If you're interested, Donald Knuth has a lot of interesting examples of bitwise majority in his 4th volume of the Art of Computing Programming. But if you set C to 1, you get OR of A and B. If you set C to 0, you get AND of A and B. Now we're talking about AND and OR. What are we missing? We're missing NOT to be functionally complete, but NOT is already there. NOT is actually here, which is the basically complement of the thing that you're sensing over there. You just need to put it, supply it back to the arrays or supply it back to some other arrays. And if you actually modify the architecture a little bit, then you also have the NOT. And now you have a functionally complete system. So it's block bitwise computation. It's not single bit, it's block bitwise. But if you rethink your algorithms right now, you can map your algorithms to this block bitwise computation engine. So I think it's very interesting, clearly. You could ask, okay, what applications could immediately benefit? And there are databases that are designed actually to do block bitwise computation. Bitviewing is one example. Microsoft has this bitfunnel engine, and bitmap indices are used, especially in databases. And we have some other examples in the paper that I'm not going to talk about. I'm going to give you one result from this bitweaving database that was designed for block bitwise computation. The goal over there was to actually do this on GPUs, but it's a great fit for Ambit substrate that I just described. And we basically see that you get significant performance improvements on queries. If, of course, you need to do the hard work to map your algorithm to the underlying engine. It doesn't come without hard work. That's the algorithm architecture co-design part. Okay, if you're interested, we have a lot more results in this paper. This paper talks about some future challenges. More recently, we've been looking at how to make this even more powerful. And this is a paper that we published last year at ASPLOS. I'm going to give you the basic idea relatively quickly, because I think it's really important to integrate these things into the system. And here we have a framework where the user, it could be the programmer, can specify any operation. It could be a convolution, for example. The user basically specifies a convolution. Either they or some tool turns it into and or not logic, and then we convert it into majority and not logic. And we use a lot of work that was developed in CAD, computer-aided design, to optimize it. There's a lot of work in that area, and I refer you to the paper for that. Now, if you have majority and not logic, you can map it to the DRAM commands that can do triple row activation, activates precharge essentially, and you can essentially generate a micro program. This is your micro program that implements a convolution, let's say, that is supposed to be executed in the memory controller. And you load these micro programs into your memory controller, and you associate each micro program with a new instruction, bulk bitwise operation new, bulk bitwise convolution, for example. Now, at the programming level, these bulk bitwise operations are called using special instructions. And basically, this integrates with existing programming models, as you can see, except it unleashes a bulk bitwise operation, right, on the memory side. And when the program executes this instruction, the micro program at the memory controller is fetched, and it executes what we have designed and accomplishes the operation, basically. Of course, it's easier than said and done. The paper talks about a lot of interesting details, like you need to make the system work, right? There's coherence, which things we will talk about basically in the adoption issues. Assuming that you make all of those work, the results are quite good, I would say. You basically outperform CPUs and GPUs on several complex NVMe operations and real-world applications. Okay, so if you're interested, there's more here, or I'd be happy to talk about it also. Okay, so these are some examples, I think, from DRAM side. There's more examples on the non-volatile memory side that I'm not going to talk about. It's very fascinating, I think. It's good that there's a lot of work going on. I will mention a couple of other things. This is also happening on DRAM as well as non-volatile memory side, but by exploiting the analog operational properties of the cells, you can also implement physical unclonable functions. You can generate truly random numbers. And there are a lot of works that maybe a lot is an exaggeration, but there are works that show that you can do this in DRAM, flash, non-volatile memory. And we've been looking at random number generation a lot, increasing its throughput, for example, integrating into the system. I think this is fascinating, basically. You really want security infrastructure on the memory side also, because if you want to execute security critical applications, you really want the security infrastructure. Okay, so that brings me to the processing near memory. We talked about processing using memory as a general approach. Processing near memory is, I think, easier to realize. That's why it's, in my opinion, happening, and hopefully it will continue happening. Here, we were going to put processors closer to memory. And when we first started looking at this, clearly this is more application-driven. What are the applications that would benefit a lot here? Whereas the previous work was a little bit more technology-driven, right? What can we do with the technology? Can we do data copying? Can we do bulk bitwise operations? Can you do matrix-vector multiplication, for example? Here, because you have a general purpose processor already, by putting it closer to the memory side or storage side, what can you gain? And then can you specialize that processor for the application? So when we first started looking at this, graph processing was very interesting. I think it's still quite interesting, clearly. And it's very much memory bound. So we wanted to design a graph processing engine in memory. And if you look at many graph algorithms, there's a lot of random memory access and little amount of computation. And we were quite intrigued by the 3D memory stacking technology, where you have a logic layer underneath memory layers. And in the logic layer, you can implement essentially processors. And clearly, this technology needs to improve even more. But you have high bandwidth and low latency access to memory layers. And other true three-dimensional technologies, monolithic three-dimensional technologies, are under development today. And this was a system we designed. I'll give you a general overview. There's a lot more interesting things because it's a full system designed for graph processing. We start with this 3D stack logic and memory. Let's call it a cube. And in each cube, in the logic layer, we put processors in order cores, simple in order cores, so that we don't violate the thermal limits. These in order cores are connected to each other via a network. And they basically can do processing on top of the data that on top of the stack, on the data stack on top of them, basically. And they communicate with each other through message passing. But we don't want to move the data. We want to send the functions to update the data. So whenever a core wants to update data in some other core's vault memory stack, it sends a message saying update your data. So this reduces the data movement, converts it to computation movement, if you will. Of course, you want to scale the system. You want to communicate, connect these cubes to each other. And what we envisioned at that time was you have an accelerator that's a big graph processing accelerator, let's say, and you connect it to a host processor just like a primitive GPU would. If you have an accelerator interface, non-cacheable, physically addressed, etc. And you offload your graph computation, and this happily computes and returns the result in the end. Of course, to make this really work nicely, you don't want to move the data or move the computation across the cubes, because those are off-chip accesses, and you want to localize as much as possible within a cube. Okay, so that's why we have more distributed systems like programming here. And it maps very nicely to graph processing, actually. I'm not going to talk about a lot of the details, but let me give you some results based on the system. This was published, you can see, about 7 years ago. There's a lot of work that improved on this, actually. Our results are kind of stale, but I'll mention that other works actually improved our results significantly. But at the time, these were the fastest or highest bandwidth memory systems, hybrid memory cube. Tesseract looks different because it doesn't have the processor memory dichotomy. Right? Processor and memory are coupled to each other, even though they're near memory processors. You're not bottlenecked by bandwidth. You expose about 8 terabytes per second to 512 processors over here. And the performance improvements on 5 graph processing algorithms are significant. It's about 13x, as you can see over here. And later work actually improved our data mapping, graph partitioning, thread scheduling, interrupt handling mechanisms, and it's more closer to 100x, if you will, today. And energy reduction is also significant. And again, later work, which we mentioned in the processing in memory primer, improved on this. So if you're interested, there's more clearly here. Let me give you something that's a bit more realizable, let's say. We did this work with Google to understand the energy consumption in consumer devices. And I already mentioned one of the key results. Data moves a lot in these workloads, and more than 60% of the entire system energy is spent on data movement. And we wanted to look at offloading functions to the compute units near memory. Now, the interesting thing is a significant fraction of the data movement comes from very simple functions in these workloads. And this is true actually for many workloads. Later, I will talk about very briefly another work where we examined more than 77,000 functions across 345 applications. And we see similar trends. There are some functions that cause a lot of data movement. If you can identify them, you can get significant performance energy improvements by implementing these simple functions in memory, either in low power cores, accelerators, or FPGA logic. In my opinion, the future is heterogeneous, so you need heterogeneity in the near memory processors as well. And in this work, we showed that you can improve performance and energy on average by 2.3x, let's say. So it's not 13x, it's not 100x. It could be optimized more, but it's not bad also just for function offloading. Okay, I'm not going to go through the details, but these are some example functions. For example, in the TensorFlow engine, packing and unpacking and quantization cause a lot of data movement. And you can refer to the paper for more detail. So there are a lot of other examples. I don't have time to cover all of them. But for example, you can have a very powerful GPU and offload the computation from a very powerful GPU to less powerful near memory GPUs. We did that with NVIDIA. And we actually did it automatically, transparently. A compiler can figure out what to offload. Of course, if you do it at the compiler level, you're at the mercy of what you can do at the compiler. So the performance improvements are not as high, but you can automatically take advantage of near memory GPUs. There's more that I'm not going to talk about. You can accelerate pointer chasing, which is a very latency bound operation today. You can accelerate prefetching. I'm going to talk about this briefly. You can accelerate weather prediction using near memory FPGAs. Approximate string matching, I mentioned that. And we have a paper coming up at ISCA where we show that, again, near memory, you can accelerate sequence to graph mapping and build a more universal genomic accelerator that can do both sequence to sequence and sequence to graph alignment. Time series analysis, which is used in many domains, which is quite interesting. Again, you can accelerate near memory and gain a lot of performance improvements. Again, graph processing, graph pattern mining. So these are just, I think, case studies, if you will. You can take a look. This was just presented yesterday by my student, where you can accelerate hybrid transactional analytical databases and analytics. Transactions are very good fit for CPUs. They're more, let's say, compute-centric, whereas analytics, where you're working on a lot of data, it's better to have a near memory processor for it. That's one of the basic ideas. And I foreshadowed this a little bit. We did this work with Google where we analyzed their neural network models. These are proprietary neural network models used at Google. I'll very quickly cover this. And the idea is existing accelerators for machine learning are very monolithic. They're very compute-centric, but they're also very monolithic. And we analyze these models and we see a lot of heterogeneity in the behavior of these neural networks in terms of, for example, arithmetic intensity and access patterns, etc. So we design heterogeneous accelerators. Some of them are compute-centric, some of them are data-centric. And if you do it nicely, you can get, again, significant performance improvements, energy improvements, 3x in this particular case. If you're interested, we have the paper online, but this is an example of the differences in the different models, as well as within a model as well. Different layers within a model have different characteristics. Different models have different characteristics also, in terms of flop per byte, for example, and the parameter footprint. So basically, because of these huge differences within a model, as well as across models, as well as dynamic execution, it doesn't make sense to have a single monolithic accelerator. It makes a lot of sense to have actually multiple different accelerators. And in this particular case, we had one compute-centric one, and we had two data-centric ones, if you will, which are near memory essentially. And you get significant performance. So this is interesting because you improve performance, you improve energy, and our results show that you can actually, the total area cost of the three accelerators is actually much smaller than the total area cost of the monolithic accelerator. So you improve on three major metrics that we care about today. But of course, it's more work right now. You need to do algorithm architecture, co-design, if you will. Okay, let me quickly talk about this one also. So FPGA based processing near memory, this already exists actually. This is a work we did with IBM. So yesterday interface we're talking about, CXL is very interesting. I think CAPI is also quite interesting actually. This is more, let's say, IBM type of interface, but it has similar properties as CXL. And the idea is you can offload computation to an FPGA board that has high bandwidth memory, and that could be your near memory accelerator essentially. And in this work, we examined weather modeling and genome analysis. I'll refer you to the paper for the details, but essentially you can customize the accelerator on the FPGA side, take advantage of the high memory bandwidth that you have, and you can see the numbers. The numbers are quite, these are from real systems, quite significant compared to state-of-the-art software, essentially, Power 9. Okay, so I think it's hopefully clear that we really need to revisit the entire stack to enable these opportunities. And there's more in this paper and these papers. That brings me to the adoption, of course. If you really want to revisit the entire stack, how are you going to adopt this, right? I think adoption issues are really important because, in my opinion, you can design any hardware. If that hardware is not used, then it's essentially not very useful hardware in the end. So that's it's no surprise, in my opinion, that these adoption issues are all related to system and software in the end. So what are the applications? What are the software? I think that relates to hardware also, because what can you enable that could be taken advantage of by a lot of software in the world? Ease of programming, clearly. How do you enable and make it work for many programmers? What are the interfaces? What is the compiler and hardware support? System and security support, coherence, synchronization, virtual memory, isolation, communication interface. I'm throwing a lot at you, but these are real issues that need to be handled, and there needs to be a lot of research on this topic. Runtime and compilation systems to take advantage of this automatically or with little burden on the software programmer, and infrastructures to assess benefits and feasibility truly of these technologies. I think it's a mountain, yes, but maybe most important barrier to us is really our mindset. Meaning today we're very much ingrained on the processor-centric designs, right? Every decision that we have made in our systems has some component that's traced back to the processor-centric paradigm. We do data mapping in a particular way so that we maximize the performance of the processor. If you do something else to maximize the performance of the near memory processor, that's going to go against what you do in the processor-centric manner today, because you're not going to, let's say, distribute a cache line to different, distribute a cache line to different banks, for example, right? Not banks, but different parts of the memory. You really want large amounts of memory in a single bank, for example, so that you can actually do near memory processing on it, as opposed to one cache line being here, another cache line being here, another cache line being here. So I think we need to really question this processor-centric mindset, and that's how we can probably change the entire stack in the end. But maybe we can get there step by step also with simple steps like row clone, like simple processors. So I think adoption issues, that's how I see the work that's being done on accelerating key applications. So these are our works, but there are a lot of other works that are happening in the field. There are a lot of applications that are being examined. I'm just showing you these. I think we need to do more of this basically to show that applications benefit. But we need to try to keep it simple as much as possible. How do you integrate into a CPU, for example? If you could call things with a single instruction, you can unleash a lot of processing and memory operations. That's great. And that's what we argued for. I mentioned this also earlier. Coherence is a thorny issue, unfortunately. How do you ensure coherence when you partition workloads between a CPU or an accelerator or a near memory engine? And existing coherence mechanisms don't work well. If you really need to satisfy coherence, you need to go on the bus. And now you're causing coherence-related data movement. if you maybe, even if you were eliminating some other data moment, like application-related data moment. So basically, we showed that existing coherence mechanisms do not scale well. So you really need new thinking in coherence. This was our new thinking, and it gets it's nice, but I think we need even simpler mechanism going into the future. How do you support synchronization? We have some work in this area, and I think perhaps the most thorny issue is virtual memory. Frankly, how do you ensure virtual memory can be extended to near memory processors? I think we really need new ideas in this area. In my opinion, actually, virtual memory needs to be rethought, even if you don't go data-centric. Today, memories are growing, they're huge, and virtual memory is not scaling, even if you don't do computation near data. Okay, let me finish with some examples with processing in memory in the real world, because if I was giving this talk again 3 years ago, these would not be there. The good thing is this is there and I can talk about it. So UpMem is perhaps the first company that I know of that has, it's a startup in France. We actually collaborate with them. I'm going to mention some of the works that you can check out. Basically, they've manufactured DRAM chips collaboratively with some manufacturer where near each bank, you have a DRAM processing unit. So you have a near memory processor inside the DRAM chip. And these are modules that we have been using in our analyses. You can see the paper over here. I'm going to mention that again. Essentially, the processor looks like this. For each bank, you have a processor. It's a reasonably deep pipeline. It's a multi-threaded processor. And you can see that it's similar to existing processors, right? It has an instruction cache, data cache, etc. It's not cache, it's scratch pads, but the same idea. Okay, so we analyze this quite a bit. If you're interested, you can read the papers that we have written. This is a shorter version of the paper, if you're interested. And we released actually benchmark suites. You can actually experiment with these. This company is very interested in actually collaborating with people, so you can check it out. I find it fascinating, I think. And there are a lot of talks that we have delivered on this topic. And okay, so FPGA-based near memory accelerators already exist. I talked about them. So this is another example, I think. In a lot of these works, I think the key question is, how do you decide what to offload to the memory side? That's true for the UpMem engine. That's true for FPGA-based memory accelerators. That's true for some other startup that you may be thinking of. And I think this is also an issue to tackle. And there are a lot of examples where near data processing is interesting, but more recently, we have examined many applications, and we developed a methodology to classify each function in an application in terms of its memory bottleneck class. It's almost automated. It's not fully automated, but if you follow the methodology, you can profile your workloads and categorize each function in terms of the data moment bottleneck. And again, this is fully open source. If you're interested in using it, we'd be happy to support it. What it enables is really to classify your function and decide whether or not you can offload it. You can use it for other purposes also, frankly. And maybe you can use it to improve your caching in your function, for example. But our goal was to enable near data processing more easily. Okay, and the paper. So more recently, Samsung announced their function in memory engine to accelerate machine learning inference. Again, this is a near bank processor. I'm going through this relatively quickly, but this is a processor that's optimized for especially multiply and accumulate. There are a lot of details in their ISSCC and other papers. And this is their instruction set architecture internal to the machine. But this is a near bank processor, basically. It's a near memory engine, very similar to UpMem, except it's specialized for not general purpose processing. UpMem is very general purpose. This is very special purpose, if you will, because it has limited functionality. Samsung and Facebook announced this near, let's say, in-module processing, where they can do recommendation systems inside this buffer chip, let's say, which is also interesting. More recently, SK Hynix announced a more aggressive version of this near bank processor, similar to Samsung's FIMDM, I would argue, but they have also very interesting support, like row-clone type of support in terms of data copying. And Alibaba also has their own version of their recommendation system, if you will. So hopefully there will be more to come, but adoption issues are really important. And can we really enable new platforms with these? We'll see. Okay, so there's a lot more to talk about, but I don't have time. If you're interested, there's a lot of lectures and talks that we deliver. So I think the takeaway is we want to be fundamentally energy efficient, and I think that requires us to be data centric. We want to be fundamentally high performance at the same time. That requires us to be data centric. I think you could change that high performance to secure, dependable, etc. I believe all of those require us to be data centric today. And we want to minimize the data moment. Again, don't take this literally, because you don't always want to minimize the data moment. Sometimes you move the data and exploit the locality. That's good. Maybe in the long term, that minimize the data moment. So we don't have time for the other parts, data-driven and data-aware, but I think they integrate nicely with this data-centric paradigm as well. If you're interested, we have tutorials related to that. Okay, let me conclude. Hopefully, I've given you a lot of examples that show that we have to, I should emphasize maybe, design systems to be truly balanced, high performance, and energy efficient to enable intelligent systems. That requires, in my opinion, data-centric, data-driven, and data-aware thinking and architectural design and across the stack design. And this way, hopefully, we can enable computation capability inside and close to memory. And hopefully, I'll be giving you examples that this can lead to orders of magnitude improvements, enable new applications and computing platforms. Of course, I haven't given you examples of that, but maybe I hinted at it, and who knows. Enable better understanding of nature, perhaps, because people have been thinking nature is not necessarily processor-centric, and I think there's a lot of evidence to that, and who knows what else. So overall, I think the future of truly memory-centric computing is bright, but we need to work hard to enable it, and that requires a lot of research and design across the computing stack. And the good news today is there are actually real systems that have these near data processors. We're not like 10 years ago or even 3 years ago. Okay. So yeah. So there are a lot of good principles that we need to think about. These are some of the principles that I talked about without explicitly naming them. But more than anything else, as I said, I think we probably need open minds. So I will acknowledge people who funded our research. Thank you. Please keep funding us. And more importantly, I will acknowledge my research group who have contributed to everything that I described over more than a decade, actually. And these are some pictures snapshotted at some point, and we have some newsletters if you want to take a look at them. Everything that I've described is available online. If you don't find something for some reason, please let us know. We open source a lot of things on our GitHub, and you can download a lot of the tools that I mentioned from that GitHub. And finally, I think you can join our classes if you're really interested in this topic. We have a lot of coverage of this. In fact, we have a specialized PIM course that we started a couple of years ago, and it's currently going on. It's going to continue. This is the current version, which has a lot of cutting edge topics, and you can feel free to join that as well. I think this is where I'll stop. Thank you very much. I'd be happy to take any questions.
Hi, I have a question. Actually, I have two questions. So first question that I feel interested about is that you show that Samsung has a processor near memory product, and Samsung as a company who produce like DRAM cells for sure. I wonder like why they prefer this approach rather than those small modifications of those DRAM architecture itself, because they are actually the company who can do both. And that's my first question. And the second question is regarding, I feel with this a lot of new computing units, paradigms, what do you envision the future of programming would look like?
Okay, so let me take the first one. The first one is, if I understand correctly, why is Samsung doing processing near memory as opposed to processing using memory, right? And the answer is, I think processing near memory is easier. It's easier to adopt because you can take a processor and put it inside the DRAM chip more easily than ensuring that you can actually do analog operations. I think analog operations are fundamentally, let's say, more difficult to get right because there are a lot of reliability issues, noise issues, variation issues that you need to handle and to make it work reliably. But if you put logic, you can make it work reliably today. So it's not, that's why it's not really fundamentally changing the design paradigm also, in addition to the programming paradigm. So that's my answer. That said, I agree that I think these memory companies are best positioned perhaps to exploit processing using memory, and hopefully they will look into it. The second question is, how do you actually change the programming to take advantage of it? Is that correct? Well, I think that's a great question. So I think there we need more research. Frankly, there's some research that's certainly being done in the hardware, software co-design and computer architecture communities, but I think there needs to be more research in the programming communities. There are multiple approaches, clearly. One is you don't change the programming model. You add instructions just like I have proposed, for example. You add an instruction that unleashes a processing in memory operation, right? I think that's not a bad model, but it has limitations, of course, right? But now the programmer expresses things in an instruction way. Fundamentally, it's, let's say, still processor-centric, although they need to think a little bit differently to be data-centric as well. So I think we really need to do more research in this area. I don't have a better answer to your question.
Yeah, thank you.
Sure, you're welcome.
I have a question here.
Okay.
Yes. I think you talked very enthusiastic about this code design across all the stacks. Normally, when we do code design, just across 2 stacks. So that's the issue, I think, with our current education system where people are focusing on one day. So then people crossing many stacks, it's hard to accept. That's common, not a question. Do you think that regarding the growing model, I don't know, you talk about foundations, like that's the foundation. So the growing model, do you think that go back to the data flow machines? It's very fundamental, intrinsic to the data-centric.
Sure. Yeah, excellent questions so far, all of them clearly. I think the first, I will comment on the education part, and I absolutely agree. I think we really need to think about our education system a little bit more to broaden people to think across the stack. And I mean, I try to do this in my courses. I teach the bachelor's course, 600 students at ETH, for example, and I talk about what I just talked about, basically. And we talk, clearly it's not easy to put it into practice, but we do FPGA programming, for example. We do part of this in the course, and I think we need to do more, no question about that. The second is data flow. Is it a good model? And I think so. I think certainly we need to look at more data-driven, data flow type of models that, let's say, are more data-centric fundamentally to take advantage of processing in memory or data-centric models. And I think like a lot of the accelerators that we see also have the data flow properties, but again, mapping it to the engines near memory is going to be something that we need to look at. We need to build a tool set for it. Sure. Yeah.
So as I was listening to your talk, I kept thinking about Ambel's law, and I think this approach seems to run into Ambel's law in every way, in kind of the worst possible way. So on the first hand, DRAM is the most consolidated, lowest margin, and also most expensive component in computer systems today. So even small incremental increases in costs are going to have a huge effect. At the same time, you can put up a bunch of applications and say, you know, we can do this bitwise stuff for these sets of applications, and that's fine. But even if you cover 100% of those applications, it's still a relatively small fraction of all computing, and then you end up with this kind of same scaling cover, economies of scale problem. So this seems like the biggest adoption problem. It's going to be very hard to manufacture things cheaply enough and to get enough of the share of the fab capacity, and then to get applications on board. Like, I'm just very skeptical. So like, how are we going to do how is this going to be an economically viable approach given the realities of manufacturing memory and computers?
Yeah, that's a great question. So I think, first of all, this is not a panacea, right? That's not going to solve everything. I think the panacea is really heterogeneity. I think we really need to have data-centric and compute-centric processors at the same time. And they're good for different parts of an application, different purposes, different applications. And that's what we have done, for example, in the machine learning accelerators. You have a compute-centric one, and you have multiple data-centric ones. So I'm not suggesting every application will benefit from just this. The second question, the DRAM part, costs. That's an excellent question. I think the earlier one was excellent also. But here, the issue is, I think we have kind of cornered ourselves to a very sad corner in the DRAM industry. Like, we are punishing ourselves in that corner for some reason. We're not able to get out of that corner, and it's unfortunate. That's the reality of life, as you said today. But maybe we need to somehow find and again, I'm not the right person to come up with a business model for this, but we need to find ourselves out of that corner. Maybe there's a space. There's a huge space we're not exploiting in DRAM and a lot of memory technologies today. It's all about cost and capacity. This is what I meant about mindset, I think. The mindset has driven us to really punish ourselves. We're not taking advantage of the technology in the best way. Whereas if we give up a little bit of cost, a little bit of capacity, and add some computation capability, maybe we'll be at a better space. And over time, maybe we can expand this more. So we're very cost-centric today, and that's really the only metric that's driving these memory systems. maybe that's not a satisfying answer to you, and it's not a satisfying answer to me also, frankly. But this is really what I mean by mindset in the end. That mindset of memory needs to change, I think. Even companies who are doing this for a living, they're cornering themselves. They're putting themselves, in my opinion, to a position where they're always cost limited, etc. But if they make a jump to a little bit, okay, let's give up the cost a little bit and let's explore the space, which is, I think, happening slowly. I don't know if it's happening in the best way. Maybe they can explore the space and we can get out of this corner, if you will. I think that's the best answer I can have to you. I know it may not be satisfying because it needs to be proven going into the future. Right?
So can you summarize like the change that I think we want to offload our workload between the accelerator and the
like between from a CPU to a processing in memory engine, you mean?
If you have like both like accelerators and the processing memory.
Oh, okay, I see. So accelerator, I guess it really depends on the accelerator in that particular case, right? Is it the GPU? Is it a machine learning accelerator? And these are also not necessarily orthogonal to each other. You can have a GPU near memory. You can have a machine learning accelerator near memory as well. So I think, so if we go back to this, okay, it's a lot of slides over here, but in this particular, bottleneck analysis case, you can extend this to more accelerators also. This was more CPU centric. Do you want to keep the function in the CPU, or you want to offload it to a general purpose near memory processor? I think you will need to extend the analysis to that particular accelerator that you're looking at. And that's one future work that builds on this topic. So I don't have a single answer to that question. It really depends on the properties of the accelerator and properties of the computation.
And like if you want also the processing memory, like what kind of mindset you have to design the algorithm?
Could you say it again? I missed the first part.
If you adopt like processing memory, like what kind of like insight or like mindset you have to have algorithm design?
Yeah, so I think that's a good question. Basically, then it becomes like, what kind of processing in memory do you have? Like if you're having block bitwise operations, you really need to rethink your algorithm such that you can exploit those block bitwise operations. And that's what we did in the paper, the SIMDM paper that I mentioned. And many algorithms actually can be rethought that way. Interestingly, there's early work from the 1960s that talk about vertical data processing, bit serial processing, for example. You can think of, fundamentally, these block bitwise operations are bit serial. So you really need to think about your algorithm in a bit serial manner, for example. So that's one example. So if you want to consider near memory general purpose processing engines like maybe Samsung or maybe UpMem, then you really need to look at, again, the properties of the function like this. This fits nicely in that particular case. Then you think about what are the bottlenecks in your algorithm and can you overcome them by offloading it to memory.
I come from the storage side of things, and of course, there's been a lot of effort to try to move computation closer to storage. And the big issue that everybody probably is aware of is security. And so it gets down to you need to have encryption and decryption near storage or near memory. And when you get to the point where you now have non-volatile RAM, is it going to be acceptable to have a non-volatile device that's not encrypted? I just wanted to hear your comment on that because it seems like it's a real tough problem for storage.
Yeah. I mean, especially with storage, I agree. I think there are even more security issues than the main memory, right? In storage, and I agree. I think that's one of the reasons why we've been exploring on the memory side these security primitives, so that we can do, let's say, hopefully encryption and decryption at some point at very fast speeds. But yeah, I mean, I agree in the end. I think these are issues that need to be solved, but maybe not all applications require that, right? Maybe we start with applications that are not as security critical. And if we enable computation over time, hopefully we will solve these problems related to security.
Just a quick comment. It's amazing what some people think needs to be secure.
But maybe there are other mindset issues over there. I don't know the specific examples over here. Yes. Yeah. I mean, you see this a lot in the genomic space also, right? What needs to be, yeah, secure and private. Yeah, but we give up a lot of security and privacy on other sides of our lives. So maybe, yeah, maybe some balancing of the global thinking about what is security to people is interesting. But again, that's a bigger problem.
So I have kind of a philosophical question for you. So this is coming from an information theorist. So back in the late 40s, people were trying to optimize communication systems, and they had a lot of different hardware components, a lot of technologies. And then along came Claude Shannon with information theory that provided a mathematical theory of communication. So now we have these incredibly complex and sophisticated computing systems that have not just the processors, but the memory elements and the storage devices and the interfaces. Do you think there's a possibility of there being some kind of overarching theoretical framework that could provide a way of assessing what the fundamental limits are that you can achieve when you put all of these things together in all of these interesting architectures and so on?
Yeah, that's a great question. I'm probably not the right person to answer that, but yeah, I think, I mean, my gut feeling is certainly there should be some limits. The question is, I think, can we describe with theory the complexity of the systems we have? And I'm not sure about that, frankly. I mean, even, for example, if you look at something like caching, very simple part of the computing system. I think it's very difficult to come up with a theory that works with many different workloads that we have today, let alone all kinds of accelerators, storage, different types of memory. Again, I don't have maybe the right mindset of a theoretician to understand that, but my feeling is very difficult.
Yeah. No, I can understand your point. Very interesting. Okay, would you mind going to your last slide?
Sure. Which one is that? Is that the conclusion slide or this one?
Okay, so I just wanted to confirm. So there were 219 slides. I think everyone in this audience would agree that there was an enormous amount of movement of fascinating data. This was a really terrific talk. So let's thank Onur again.
Thank you.
And I gather that most of this material, if not all, you said is available from your website, including slides and the video and so on. Or will be.
Yes. I'm happy to make these slides available. I'm happy to also send it to you, the conference organizers. You can also put it on the website if that's.
Keep that in mind if you want to revisit some of the enormous number of interesting points that were made. Okay, well, thank you again, Onur.